Hi, welcome back to the Cuzzy Sound channel, part 22 in the series all about my Project 12 DIY modular analog synth. In this particular video we're going to be looking at the Attenuverter module. Now, the theory behind this circuit I got from the XII website. He goes into all the detail about how the circuit works, and it's really useful, but not as difficult to understand as you might think. So I do recommend that you go and check out that web page. I'll put the link down in the description. What I'm going to do is give you a summary of how the circuit works, so just enough so that when we start to use it in anger in the synth, we have a reasonable understanding, or at least a basic understanding of what's going on. So I'll go through some of that. I'll then show you how I put my particular module together, and then as usual we'll go and have a look at a brief idea of some of the things that the circuit can do. So let's start with a brief summary of theory. Don't panic. This is not going to be difficult or intense. I'll keep it as straightforward as I possibly can. This is the basic attenuverter circuit. So what it is, we have an op amp here, and it's set up in such a way that it acts both as a non-inverting and an inverting amplifier, dependent on the position of the output from this potentiometer. So we've got an op amp, and then on the inverting side we've got 100k and 100k on the feedback. So basically there's at that point, with everything balanced, we've got a unity gain. And then on the non-inverting input we have the potentiometer going between the input and ground. Now what happens is, as we move the potentiometer, we move from a non-inverting phase into an inverting phase on the output of the amplifier. If we draw a graph of what the output looks like, then this is what we will get. So the horizontal axis is the position of the potentiometer knob, and then the red line is the output. So in this top phase here we are in a non-inverting mode, and in this bottom left part of the graph we're in the inverting mode. So you can see, as we start to move the potentiometer, we go from a full positive output down through 0, and then we start to invert the output and increase the output itself, its amplitude. So we're kind of increasing the voltage that way, but we're increasing the negative voltage that way. And then around about the center here you should get 0 output. So this part of the graph is an attenuator, this part of the graph is an inverter, hence attenuverter. Now there's a issue, or potential issue, with this very simple design, in that the transfer point between non-inverting and inverting through 0 can be quite harsh. So when you're actually using the synth, you can inadvertently overshoot and go from very quiet non-inverting into suddenly inverting the signal, albeit it'll still be a bit quiet depending on how vicious you are with turning the knob. But there is a simple way around this, and a slight modification to the basic Attenuverter circuit. I'm in the background throwing bits of paper around. we'll solve this, and the way we get around that is by putting these load resistors either side of the potentiometer. Now, this is a technique that is sometimes used to convert a linear potentiometer, which is what this one is, into a kind of quasi or pseudo logarithmic potentiometer. It's not a true log potentiometer, but it does change the shape of the output. So what I'm going to do now, I'm going to attempt to do this on the fly. I'm going to try and draw what the changed output would look like. So that's our modified circuit with just the addition of those two load resistors. Go back to our original graph. So with just the straight linear potentiometer, you get a straight line, which is indeed a linear output. But if we add those load resistors, what happens to the output is it goes something like and we get kind of a reverse S curve. So what happens is we get more finesse around this transfer point, so we don't get a sudden jump from non-inverting to inverting. You can change the shape of this, which basically moves it further away or closer to the linear line, by changing the value of those two load resistors. Now, I did play around with a few values and found that 47k, which is what it said on the diagram, actually worked best for me. It's also what Casutronics came up as probably the most useful value. So there we go. That's the very basic theory. If you want to know a lot more about how it's calculated and how things work, then go follow the link and check out the Casutronics page. So what I'm actually going to build is this, what is called a precision attenuverter. Now, the way that I translated this into a module for myself is I've used a TL074 op amp, which gives me 4 op amps in one chip. So I've got a quad attenuverter, and my circuit diagram for the quad attenuverter looks like this. So as you can see, it is simply 4 of those precision attenuverters running independently from the chip. A thing to note is that the power supply is dual rail, so there's plus and minus 12 volts, and obviously 0 ground in between. So you do need a dual rail power supply for this one to work. But it's a relatively simple circuit, really. And the layout I used on the strip board looks like this. So there's the chip, and then you've got just a bunch of resistors, and then there's a whole load of sockets, jack sockets and pots, all wired up to the board. Now, the circuit diagram and the layout diagram will be on the XII Sound Dropbox folder, and again I'll put a link down in the description for that, so you can click through to that and get some decent images of the circuit and the layout if you want to go and build your own, which I hope you do. And if we look at what it actually looked like when I built it, this is the back of the panel, and so you can see it is relatively straightforward. It's just lots and lots of soldering of sockets and pots, really, and a little bit on the board. The front of the panel looks like this. So like I said, there's 4 of them there, and they operate independently. They're not linked in any way, so you've got 4 independent attenuverters. The left socket is the input and the right socket is the output, and then you've got the potentiometer control in the middle. So with the potentiometer set central, there should be no output. Hard right, and you've got full non-inverted. Hard left, and you've got full inverted. So let's go and have a listen to what that actually sounds like on the synth. Before I demonstrate the function of the attenuverter, I want to talk through the patch I've got set up, because as you will see later, it's important to know where the signals are coming from and where they are going to. So we'll start with a sound source, and for that I'm using a sawtooth oscillator, a VCO, but I'm not providing any control voltage, so I've just got a single tone generated as a saw wave. That saw wave is then going down and into a VCF, voltage control filter, and then the output from the filter is going via a mixer so I can record it on the video soundtrack. Here I've got an envelope generator, an attack release envelope generator that is set to loop, so there's no external trigger for it, so basically it's just looping around its own envelope shape, so it's self-triggering. And then the output from the envelope is going to the input on the attenuverter, and the output from the attenuverter is going via this splitter block. It's just a passive splitter. One output from the splitter is going to the CV in on the filter, so that is controlling the cutoff on the filter, and then a copy of that signal is going into the oscilloscope so that we can both see and hear the effect that the attenuverter has, because the signal that the scope is seeing and the CV on the VCF is seeing is the envelope signal after it has passed through the attenuverter and therefore has been affected by the control on the attenuverter. So we're going to move in closer on the oscilloscope so we can actually get a clearer view of the trace. We can see as well as hear what's happening. I'll probably dim the lights as well a little bit, make it a bit easier to see. So you should be able to see, scrolling across the screen, you've got the very sharp attack and then a little bit of roll off for the release. The control, it's a bit difficult to see because I've turned the light down so we can see the scope, but the control on the attenuverter is hard right, so it's full non-inverting at the moment. Now if I start to turn that control, you should be able to see the peak of the output dropping, and you should hear the effect on filter changing. And as I approach center, we're pretty close to zero. Now if I keep going left, what we start to see, you should start to see the peak reappearing, but this time it's below the center line and it starts to get bigger and bigger and bigger until I'm now hard left, and we have an inverted version of our envelope shape. So yeah, there's the inversion. But you're saying, okay, so what's happened to the sound? How come the sound hasn't come back in? Okay, we are controlling, the CV is controlling the cutoff frequency of the VCF. So at the beginning we were using the envelope shape to open the filter to increase the frequency. So I've got the cutoff on the filter turned down. But we've now inverted the signal, so we're going to invert the effect. So what we should be doing now is closing the filter, but because I've got it turned down, it's already closed. That's why you're not hearing anything. If I turn up the frequency on the filter, we should get to a point where so now you can hear it, and what we're hearing now is we've inverted the envelope CV signal, so that CV control on the filter is now closing the filter rather than opening it. So we should be able to get an attenuation of our inverted signal now. And we'll get to a point where what we're hearing is the output from the filter, because remember now we've turned the frequency up, so we don't have to open the filter to hear the saw wave. What we're hearing now is the saw wave coming out of the filter. So if I keep going, it doesn't seem to have that much effect on the sound, because once again we're now kind of opening the filter, but I've already got it open. So to get back to where we came from, I have to turn the filter down again. So I think the thing to note with this is that if you're doing this sort of thing with it, and you think, oh well, that's not having an effect, retrace your patch and think about what the control voltage is trying to do. If it's trying to close a filter that's already closed off because you've got the frequency turned down, of course you won't hear an effect. It'll sound like nothing's happening. And inversely, we are talking about inversions here, when I went the other way, because I had to open up the frequency in order for the inverted signal to close it down again, once I went back into a non-inverting, we just got it coming through all the time because it was trying to open a filter that was already open. Hopefully I've not confused you with all that, but it's just one brief example of one of the uses for an attenuverter. So if you think you can make use of an attenuverter, I've given you all you need. So go on, have a go. Build your own.